Welcome to RaWMachines, a journey into the most remarkable industrial processes around the world. What truly holds a vessel weighing hundreds of thousands of tons steady in the open ocean? Is it just the anchor, or an entire engineered system working behind the scenes? In this episode, we follow the full life cycle, from shipbuilding and anchor chain manufacturing to anchoring mechanics in real-world marine operations. Let's uncover how it all actually works. In anchor chain manufacturing, the entire production line operates continuously, from raw material processing to final inspection, where each link is required to achieve absolute strength under heavy loads in marine environments. High-strength alloy steel is introduced in the form of round bars with controlled compositions of carbon, manganese, chromium, and silicon to ensure tensile strength and fatigue resistance. The material is then cut into segments according to the design length of each link, with strict dimensional tolerances maintained to ensure uniformity throughout the entire chain. The steel segments are fed into induction furnaces and heated to approximately 1,200 degrees Celsius. Once the metal reaches a ductile state, it is immediately transferred to the forming stage to prevent heat loss. Under the force of hydraulic bending machines, the steel bars are wrapped around a mandrel, forming the characteristic oval shape. At this stage, new links are not formed separately, but are directly interlocked with the previous link in sequence, ensuring a continuous chain is created during production. At the joint, the open ends of each link are placed into a flash butt welding machine. A high electrical current passes through the contact surfaces, generating a localized molten zone, which, combined with high pressure, forms a solid welded joint. Although the process occurs in a very short time, it directly determines the strength of the entire link. After welding, excess material, flash, is removed by trimming and grinding, and the surface is further processed to restore geometric accuracy and eliminate stress concentration points. Following welding, a stud is inserted into the center of the link using automated feeding equipment and secured by hydraulic pressing. The stud stabilizes the link geometry under heavy tensile loads and helps prevent twisting and deformation during operation. In high-grade chains, the stud may also be fixed by tack welding to ensure it does not shift. The chain is then fed into a continuous heat treatment line. During quenching, it is rapidly cooled in water or oil to increase hardness and wear resistance. Immediately after, tempering is carried out at a lower temperature to adjust the crystal structure, reduce brittleness, and improve toughness. Heat treatment parameters, including temperature, time, and cooling rate, are strictly controlled to ensure consistent mechanical properties along the entire chain length. After heat treatment, oxide scale and residues form on the surface. The chain is cleaned using a high-pressure shot blasting system, where steel shots continuously impact the surface to remove contaminants and create uniform roughness. This process also helps reveal surface defects, such as cracks or porosity, before detailed inspection. The chain then moves to the inspection stage, where tests are conducted according to strict standards. During proof testing, the entire chain is tensioned on a test bed under high loads, typically reaching 70 to 80% of its design braking strength to verify its actual load-bearing capacity. At the same time, non-destructive testing methods such as magnetic particle inspection or ultrasonic testing are applied to examine welds and internal material integrity, ensuring no hidden defects are present. After passing inspection, the chain proceeds to surface protection. The entire chain is either immersed in hot bitumen or coated with specialized epoxy, forming an effective corrosion-resistant layer for marine environments and reducing friction during anchoring operations. In the final stage, the chain is measured for overall dimensions, classified by production batch, and marked for identification on each segment. Technical information such as steel grade, design load, and applicable standards is fully recorded, along with classification certification before the product is released. From raw steel bars to a finished anchor chain, the entire production process is a combination of precision machining, metallurgical engineering, and strict quality control systems, ensuring that each link can operate reliably under extreme loads and harsh ocean conditions. Have you ever wondered what truly keeps a vessel weighing hundreds of thousands of tons stationary in the open ocean? Is it just an anchor or something more? Across vast oceans where winds and currents are constantly acting on the ship, massive vessels, floating cities, can remain in position for extended periods. This stability does not come from a single anchor, but from a precisely engineered system in which the anchor, the chain, and the seabed interact to generate holding force. In reality, if an anchor is simply dropped into deep water, it is almost incapable of holding the vessel. Improper handling during anchor recovery can even generate dangerous loads on the ship's structure. The key factor lies in the anchor chain, a component with significant mass that absorbs and distributes forces throughout the entire system. Anchor chains on large vessels are not ordinary chains. Each link can weigh over 130 kilograms, and the entire chain may extend beyond 300 meters, with a total mass reaching tens or even over 100 tons, often exceeding the weight of the anchor itself. When deployed, most of the chain rests on the seabed, generating friction and acting as a massive counterweight. During anchoring, the vessel does not simply drop the anchor, it deploys a sufficient length of chain to form a natural curve known as a catenary. This shape allows forces from wind and waves to be distributed along the chain rather than transmitted directly to the anchor. When the vessel is pulled backward, it must first lift part of the chain off the seabed, significantly reducing the applied force. By the time the force reaches the anchor, it is nearly horizontal, allowing the anchor to penetrate deeper into the seabed instead of being pulled out. The length of chain deployed is not fixed, but determined by the scope, typically 5 to 7 times the water depth, and increased further under strong winds or rough seas. This ratio ensures an optimal pulling angle for effective anchoring. However, in extremely deep waters, such as the open ocean with depths of several kilometers, anchoring becomes nearly impractical, as the required chain length would be excessive, overloading the windlass and imposing dangerous stresses on the ship's structure. In such conditions, vessels do not rely on anchors, but instead drift or use dynamic positioning systems. These systems use computer-controlled thrusters distributed around the hull to continuously adjust the vessel's position without contact with the seabed. When anchoring in suitable depths, the length of chain deployed is controlled using a traditional segmentation system. The chain is divided into standard sections called shots, each approximately 27.5 meters long and marked with color codes for identification. During deployment, the officer at the forecastle observes and counts the number of shots released, reporting back to the bridge so the captain can adjust as required. When the anchor reaches the seabed, it does not immediately hold the vessel. Initially, it rests on the seabed surface. To activate its holding capability, the vessel must slowly move astern. This pulling force causes the anchor to rotate and self-orient, allowing its flukes to penetrate the seabed. As the load increases, the anchor embeds deeper into sand or mud, generating substantial resistance. This mechanism enables a single anchor to secure a vessel of immense size. When departing, the process is reversed. The windlass begins retrieving the chain, gradually lifting it from the seabed. In the initial stage, the anchor remains embedded in sediment. As the vessel moves forward toward the anchor position, the pulling angle shifts from horizontal to near vertical, eventually extracting the anchor from the seabed. Once freed, it is hoisted above the water and secured at the bow. The anchor, therefore, does not function independently, but as part of an integrated system involving chain weight, force geometry, and seabed conditions. It is this interaction that allows massive vessels to remain stationary in the open ocean without any fixed structure.
Dali ha. Dali, dali. Tabi muna tayo. Tabi muna, Bert, kasi may lupit. Sige, Arya. Tandaan lang ha. Dali ha. Dali, dali, dali.
Balito, pasok yan.
Pang YouTube to. Mga batang Laguna, hindi Cavite. Bira, bira.
Within a vast shipyard, where cranes operate continuously and steel is processed without pause, a vessel gradually takes shape through a tightly controlled construction process, from digital design to full assembly. Before production begins, the ship is fully developed in a digital environment. Naval architects define the hull form, calculate hydrodynamics, displacement, and load distribution. The structure is analyzed in accordance with classification society standards to ensure structural integrity. At the same time, all major systems, including propulsion, electrical, radar, and communications, are integrated at this stage, forming the basis for detailed construction drawings. During fabrication, steel plates are cut using CNC technology, then assembled and welded into panels. These are further built into subblocks and completed as large blocks. Throughout this process, piping systems, cable routes, and watertight bulkheads are installed in parallel within each section. Each block undergoes individual inspection before final assembly. This modular construction approach allows multiple processes to run simultaneously, improving schedule efficiency and ensuring quality control at each stage. Once completed, the blocks are transported using SPMT systems and positioned for assembly. Each section is aligned within millimeter tolerances before structural welding. Welds are inspected using non-destructive testing methods to ensure strength and watertight integrity. After hull erection, the ship's structure is fully formed. Main equipment is then installed in the engine room, including the main engine, shafting system, and auxiliary systems. Electrical, control, radar, and navigation systems are integrated and connected to the central control system. All systems are then commissioned and tested internally to ensure synchronized operation before final outfitting. Once all structural work and system installations are complete, the vessel enters its final outfitting stage prior to launch. The hull surface is cleaned using high-pressure equipment to remove rust and contaminants. A corrosion-resistant primer is then applied to prevent oxidation, followed by controlled coating layers that ensure adhesion, thickness, and long-term protection in a marine environment while also completing the vessel's color scheme and identification markings. All technical systems undergo final inspection and calibration. Electrical, control, radar, and navigation systems are commissioned and tested to ensure stable and integrated operation. A comprehensive technical inspection follows. Coating thickness is measured to meet standards, while critical mechanical components, including the propeller, shafting, rudder, and C-valve systems, are checked for alignment, installation tolerances, and operational performance. Hull penetrations and watertight systems are thoroughly verified to prevent leakage during service. Before launch, fuel tanks, ballast tanks, and sealed compartments are subjected to tightness and pressure testing. Safety systems and life-saving equipment are also inspected to ensure readiness for initial operation. Once all requirements are met, the vessel is moved to the launch site. A naming ceremony is often held beforehand, marking the official completion of construction. The ship is then launched using slipway systems, or floating docks, under strictly controlled conditions to ensure structural safety. This stage concludes the construction phase, transitioning the vessel into testing and real-world operation.
Hijo y Espíritu Santo descienda sobre esta nave.
Es un honor hacer uso de la palabra en esta histórica y significativa ocasión. Y permítanme iniciar las mismas expresando un especial reconocimiento al señor Presidente de la República por presidir esta ceremonia, a la primera dama de la nación, quien será las distinguidas autoridades políticas, civiles, diplomáticas y militares nacionales y de países amigos que nos acompañan. A través de esta larga singladura
In modern shipbuilding and marine repair, airbag technology is not only used for launching, but also serves as an effective solution for hauling vessels ashore for maintenance and repair. At the shipyard, the barge Tri Mukti 33 is brought ashore using an airbag system, a method that employs high-pressure rubber cylinders in place of traditional solutions such as slipways or floating docks. Given its large dimensions and weight of thousands of tons, the entire operation requires strict control over load distribution and hull movement. Specialized rubber airbags are positioned beneath the hull using excavators, arranged transversely at calculated locations to ensure even load distribution. The hauling ground is inspected for flatness and load-bearing capacity to prevent localized settlement. Once the system is ready, the airbags are inflated, with pressure gradually increasing to lift the hull out of the water and transition it into a state fully supported by the airbag system. When the hull reaches equilibrium, towing cables are connected to bulldozers or winches to control the hauling speed. The airbags are continuously adjusted to ensure stable movement along the intended axis throughout the entire hauling process. Under the combined effect of pulling force and the airbag system, the barge begins to move gradually up the shore. Friction between the airbags and the ground generates heat and dust. However, the vessel's motion remains within controlled limits. Airbags at the rear are retrieved and reused, while those at the front continue to provide guidance and support. Once the vessel is fully brought ashore and stabilized in position, hull surface treatment is carried out using ultra-high pressure UHP water jetting technology. Spray robots are positioned close to the hull using cranes, applying high-pressure water jets to remove old coatings, rust, and marine growth without affecting the steel structure. On large surfaces, the robots move horizontally. In hard-to-reach areas, self-propelled magnetic crawler robots adhere to the surface and operate vertically, ensuring uniform cleaning across the entire hull. After completion, the steel surface is inspected to confirm that it meets the required condition for the next coating stage. In parallel, maintenance of maritime buoy systems is carried out offshore. Buoys are lifted over the vessel's side and deployed into the water together with anchor chains and sinker weights to secure their positions. Retrieved buoys are cleaned and inspected, while corroded chain sections are replaced to ensure stable operation. Once completed, the buoys are prepared for redeployment, contributing to the accuracy of navigational aids and ensuring the safety of maritime routes. The entire sequence, from airbag-assisted hauling and hull surface treatment to buoy maintenance and deployment, is carried out under strict technical procedures, requiring precise coordination between equipment and personnel to ensure reliability and safety in marine operations. From the first steel plates in the shipyard to a fully completed vessel launched into the water, operating at sea, anchoring safely, and eventually returning for maintenance and repair. The entire journey reflects how modern maritime engineering is a precise integration of mechanical engineering, metallurgy, automation, and highly coordinated construction processes. A ship is not merely the result of assembly, but the culmination of thousands of interconnected processes, from digital design and hull fabrication to system integration, anchor chain manufacturing, anchoring mechanics, and post-deployment maintenance. Each stage is strictly controlled, where even the smallest deviation can impact the entire system once the vessel enters real-world conditions. Every detail, from a single weld to an individual chain link or the entire hull structure, must meet rigorous standards of strength, precision, and long-term performance under the harsh conditions of the ocean. It is the seamless coordination between technology and human expertise that enables these massive steel structures to leave the shipyard, venture into the open sea, and operate reliably throughout their service life. Thank you for staying with us until the end of this story. If you enjoyed this content, don't forget to like, share, and subscribe so you won't miss our next stories. RaWMachines, thank you, and see you in the next episode.